Hi everyone, my capstone project is about forecasting US home price index levels at the county level while incorporating climate hazards and turning that into something decision useful for lenders and insurers. Here's the core idea. Climate risk doesn't just cause physical damage, it can also flow through the financial system. Higher hazard exposure can lead to higher losses, which can affect insurance availability and premiums, which then impacts affordability and eventually housing prices and collateral risk. So instead of building just a model, we are building an early warning style monitoring tool that can flag where housing affordability and risk could worsen. The practical question I want to answer is how do you use an XGBoost model on panel data to forecast next year home price index levels with climate hazard processes, and why does it matter than a simple trend line? First step, we need to define the prediction target correctly. So instead of predicting a 10-year change, I narrow the target to a next year HPI level. So that turns the problem into a clean one-step supervised learning setup. Then if you want multiple years ahead, like let's say from 2026 to 2030, we generate that using recursive rollout, meaning the model's predicted value becomes the next input. So this is a key best practice. Predicting the next level is usually more stable than long horizon differences, but the trade-off is that recursion can accumulate error, which I handle transparently later. So second step is building features in three buckets: housing, macro, and hazards. The dataset contains county year rows from 2000 to 2020. The features fall into three buckets: housing market state, current HPL level, macro context, it's a GDP, unemployment, property rates, population, and mortgage purchase counts and amounts. The last one is climate hazards, flood, fire, hurricane, heat, and drought proxies. So the hazard score trick is instead of feeding raw hazard variables directly, I build interpretable composite hazard scores using standardization and averaging. For example, flood score combines flood frequency, flood property, damage, and flood duration. Fire score combines with is fire frequency and fire size. Hurricane score combines hurricane death and hurricane damage. Heat drought score combines heat stress index and drought index. So why is this useful? It standardizes different units into a single comparable scale and produces features you can explain to a non-technical stakeholder as relative hazard intensity rather than the raw event counts. So there are also macro features. A second best practice is levels alone can miss regime shifts, right? So I add year over year deltas and percent change for macro variables like change in unemployment and percent change in GDP and mortgage activity to capture momentum. So the next step is preventing leakage with a time-based split. So because this is a panel time series model, I use a strict time split. So for train data set, I use from 2000 2014, for validation from 2015 to 2017, and for test data, I'm using from 2018 to 2019. So this avoids a classic mistake where you accidentally train on the future and also preventing data leakage. So the next step is handling missingness and fixed effects properly. So real county data has gaps. So I use median imputation based only on the training set, best practice to avoid leakage, right? So then I encode counter fibs with one hot encoding, which effectively adds counter fixed effects. This is important because counties have persistent structural differences and fixed effects let the model learn them without needing heavy like engineering. So the next step is training our machine learning model XGBoost and evaluating it honestly. So I use XGBoost because it handles nonlinear interaction very well. For instance, hazards might matter more when affordability is already stressed. So in my results, the model performs strongly on pre-2020 data. Validation RMCE is about 30 with R squared around 98. Test RMC is about 39 with R squared around 97. So on the normal regime, it tracks next year HPI levels really closely, as we see from the metrics. So when I plot the test years, 2019 and 2020 as national means, the predicted mean is very close to the actual mean, only a few index points off. So step 6 is forecasting starting from 2021 to 2030 using scenario-based exogenous simulation. So here's the biggest real world learning. After 2020, I don't have real future macro and hazard inputs in my data set, so I can't claim a pure, let's say, crystal ball forecast. So instead, I generate a scenario condition forecast. I start from 2020, then simulate each country's macro and hazard variables forward using its historical median year over year change. So then I roll the model forward recursively year by year. And this framing is honest and still useful because it answers if macro and hazard drivers evolve like their historical median drift, what path does the model imply for HPI, right? So next step is interpretation of the charts, what we have to analyze them. The first chart is show national mean history plus forecast. The national mean rises steadily and under the simulated scenario continues rising through up to 2030. The second chart, we have a test period 2019 and 2020. Predicted and actual national means are close, as you see from the chart, showing the model captures near-term movement well in the pre-2020 regime. The next chart, it's just 2021, 2024 versus government HPI. It's a comparison. This is a critical reality check. The model preserves the ranking and general direction well, but it underestimates the post-COVID level jump, especially 2022, 2024, right? That's consistent with the limitation that the model was trained mostly before COVID era, and the scenario simulation will not capture sudden shocks like stimulus, supply constraints, and rapid rate change. The next chart is about forecast and actual base scenario. Since we don't have ground truths, metrics here are not accurate. They measure how far the model scenario path deviates from a simple baseline train scenario, basically a diagnostic for how much climate macro signals push the forecast away from historical trend. Based on this analysis, the big takeaway is the best practice isn't just building a powerful model, it's building a forecast you can defend. So I used time-safe validation, interpretable hazard scores, and scenario-based forecasting so the output is transparent, explainable, and usable for monitoring risk even under uncertainty. Thank you very much for your attention.